Welcome to Gradient Daily. Today, we examine a new paper from Microsoft and the Trellis project titled Structured 3D Latents for Scalable and Versatile 3D Generation. Right now, the spatial computing ecosystem is fractured. Game engines, VR platforms, and industrial simulators require strictly incompatible 3D data formats to render environments. If an asset needs to move between these ecosystems, its structure must be rebuilt. Watch closely how this rotating object shifts from a hollow geometric wireframe into a dense, continuous, light-scattering cloud. The underlying math defining the shape in these two states is completely different. Current generative AI models share this limitation. They are hard-coded to output exactly one of these specific formats. Training a model to output wireframes means it cannot generate volumetric fields, locking that asset into a single software pipeline. The researchers address this with SLAT, which stands for Structured Latent Representation. SLAT functions as a universal mathematical space for 3D modeling. It captures raw geometric and textural information in a format independent of any specific rendering engine, allowing it to be translated into whichever downstream format a developer requires. By separating the generation step from the rendering step, developers no longer have to train separate models for every 3D format. They can pool their compute to build a single, massively scaled generation network. SLAT targets three rendering formats. First, the polygon mesh explicitly defines objects using interconnected points and lines. Second, neural radiance fields replace those strict boundaries with a continuous volumetric field. Third, 3D Gaussian splatting forms volumes using millions of overlapping colored ellipsoids. These formats require distinct optimization targets. A mesh calculates surface boundaries. A NeRF solves for continuous implicit fields, and Gaussian splatting tracks discrete geometric entities. A universal generative model requires an internal latent architecture that commits to none of these structures, yet stores enough precise geometric data to perfectly synthesize all three. The SLAT architecture starts with an empty 3D bounding box, progressively filling with a sparse array of small cubes to form a hollow outline. By keeping only these outermost surface cubes active, memory cost drops from a cubic to a quadratic scale, making high resolution viable. With the rough geometry established, the architecture adds a second layer, high-resolution appearance features extracted from a pre-trained 2D vision foundation model. These dense multi-view 2D feature maps anchor into the 3D space. Complex color and texture data from flat images project directly onto the active cubes. The grid then splits into two layers. The sparse grid explicitly dictates geometry, while injected 2D features govern textural appearance. This hybridized, two-pillar data structure provides the mathematical framework necessary to carry structural and textural information down to the specific decoders for meshes, NeRFs, or Gaussians. To build these SLAT grids from scratch, the generative model must predict the correct spatial layout and texture features based entirely on an initial text or image prompt. Traditional diffusion modeling maps pure noise to structured data over an erratic, curved path, requiring computations at multiple checkpoints. In contrast, rectified flow connects these empirical distributions with a perfectly straight and direct line, bypassing the complex curved path entirely. By perfectly straightening this complex probability path, the rectified flow approach dramatically reduces the number of computational steps required during the inference phase. Microsoft combined this equation solver with a transformer architecture, tailoring it specifically to process the distinct layout of the SLAT grid. This computational efficiency was mandatory. Training a model on a dataset of 500,000 diverse 3D objects requires massive compute, and standard diffusion curves would have been prohibitively slow. They scaled this architecture up to 2 billion parameters. This massive capacity allows the network to memorize and accurately reproduce ultra-high-frequency geometric details across thousands of distinct object categories. Coupling a straight-line equation solver with a heavily scaled transformer bypasses traditional compute bottlenecks, allowing the generation of native 3D latents at exceptionally high resolutions. Because SLAT generates assets in a rapid feed-forward pass, it supports interactive workflows that previous generation methods could not. Look at this completed SLAT grid. A bounding box isolates specific volumetric coordinates for localized editing. Running the rectified flow transformer exclusively within that region recalculates its shape based on new inputs, while the surrounding grid remains static. This localized editability proves the network has learned genuine spatial awareness regarding the physical location of components, rather than just memorizing flat 2D viewpoints. Compare this efficiency to previous methods like score distillation sampling, used in models such as Dream Fusion. Those systems required per-prompt optimization to build a single radiance field. SLAT infers the geometry directly. Quantitatively, SLAT surpasses recent scaled models in standard FID and clip evaluation metrics across both image to 3D and text to 3D generation tasks. There are geometric limitations. Because the network relies on a feed-forward dataset of 500,000 objects, its topological imagination is strictly bounded by the structural variety present in that specific training data. Architecturally, relying on a sparse spatial grid introduces a quantization trade-off. Discretizing the space limits the model's ability to render the ultra-smooth surfaces achievable by purely continuous implicit fields. To summarize, SLAT establishes a universal mathematical intermediary for 3D data. Its 2 billion parameter rectified flow architecture accelerates inference, and decoupling the generation step allows developers to render high-quality meshes, NURFs, or Gaussians from a single source asset. Thank you for watching Gradient Daily. If you found this breakdown valuable, please engage with us and join us tomorrow as we deconstruct another major paper in machine learning.